Good afternoon, everyone. Can you hear me? Could I have the, whoever has the mic, I tend to walk around, so that would be helpful. Can you hear me all right? There we go. So, good afternoon, everyone. I'm Eric Malice, Chief Marketing Officer of Lincode. I'd like to start off by first thanking everyone who helped put this together and everyone who took time out of their day to be here. You know, we're all very busy in this world, and so a lot of people who put this on, I know, are very passionate about their work and put a lot of time into it. So thank you for all being part of this ecosystem and this family. So a little bit of background on me before we get started. In addition to being the CMO of Lincode, I actually advise a number of startups on growth strategies and value proposition and messaging. I'm an attorney. I spent a number of years working at law firms like Cooley and Kirkland & Ellis in the United States, helping companies to structure and grow. I'm a professor of law at Santa Clara University. I'm a co-founder of Talus Partners, and I've spent a number of years in different sectors, the private sector, government as well, including the White House and the previous administration, the State Department, and a few federal judges as well. My passion has always been around how technology and innovation come together to truly solve problems that we need to solve as human beings, to help businesses grow and be more effective while thinking of the larger picture as where we're headed in terms of humanity. So it's my honor to be here today to share just a few words, and hopefully we'll have time for a few questions at the end here. If we don't, I know that at the end of my presentation, we'll take a short break, and there'll be some people standing at the back with some pieces of paper and some pens. So if anyone has a question, but perhaps they don't necessarily want to raise their hand, you're welcome to write it down, and then someone will be collecting those, I think the same people distributing. And then during the panel discussion, we can take a few of those questions and ask them to the group as well. So with that, I'll begin talking about AI for visual. So agenda, for the next 30 minutes, what I'm going to cover. Number one, I'm going to briefly talk about smart factories and from a market perspective. I should say, by the way, given my background, I'm not a technologist at heart. I'm a businessman and a strategist who works closely with technology companies, so I often serve as the bridge between the really smart techies and the end users and the business advisors and the investors. So I have sort of a generalist knowledge, but there are many other people in the room here, both the presenters and the audience, that are much more well-versed than me from a deep technical standpoint. So I'll be just giving a brief overview on where we are with smart factories, sort of from an overall global marketplace perspective. Then I'm going to talk about some of the challenges that companies are facing when growing in today's world of Industry 4.0. And then I'm going to jump specifically into quality inspection. I'm going to talk then about visual inspection with machine learning and how that's really changing the way. Then I'm going to go a little bit deeper into artificial intelligence and then talk about how AI-powered visual inspection is really the next leap forward. I'll give an example of that, specifically with respect to dimensional analysis, and then talk a little bit about the Lincode solution as it applies here. I don't know if this clicker is working, so it's a bit slow. So first, right off the bat, so smart factories. It's actually projected to be a $600 billion industry. That's with respect to the global smart manufacturing market by 2023. And the reason for this is that there are a number of technologies included, from artificial intelligence, data analytics, machine learning, robotics, predictive analytics, and automation in terms of the real next level and how these different technologies are talking to each other. I don't know if you know, but 3 out of 4 manufacturers today already implement some type of smart factory technology. And yet still, 86% of chief innovation officers from some of the largest manufacturing companies around the world are still focused as one of their primary tasks on how they can increase smart factory technologies. So despite the fact that the majority of companies have already taken a step forward, they also recognize that we're still at the very beginning, the inception of this new revolution. Over 1/2 of manufacturing companies around the world have allocated over $100 million to building smarter factories. So these are obviously the larger companies that have taken this step forward, and many of the smaller companies are not quite at this numbers, but this presents sort of a scope of the breadth here in terms of how people are looking to expand. So what are some of the challenges, right? There are a number of challenges when it comes to smart factory, Industry 4.0, from increasing pressures in the marketplace to limitations of data that are needed, decrease in skilled labor and projected increasing decreases in skilled labor over time, as well as integration issues all across the map. Many people are familiar with those. I'm going to take those challenges and boil them down to really two buckets. So number one, emerging technologies. We are living in a world where technology is changing faster than ever, faster than ever. So companies are faced with a really hard challenge. On the one hand, technology is getting more difficult, and consumers have this expectation that I want everything now. In the world of Amazon, nobody can wait anymore for their product to be delivered to them. So whether it's B2B or B2C, there's this increased pressure on all manufacturers to be able to develop more products effectively in shorter time frames. So the number one business challenge that manufacturers identify when it comes to where smart factory solutions can actually enhance business performance, the bottom line, what we care about. Any guesses what the number one smart factory technology is? Or in terms of the actual challenge that smart factory can help? Any guesses? This is based on surveys of CEOs and CIOs and CTOs of the largest manufacturing companies in the world. I'll tell you, quality management. The ability to produce products as they're intended to be produced at scale. So, how do companies address quality issues today? Generally in two ways. Number one, there's manual inspection. So from the parts you're receiving from your vendors to the actual production line, labeling properly and sending it off. Typically, for many companies, this is still a manual process to check for components, the text is legible, that the angles and the geometry of the pieces installed, there's no scratch or defects, the right parts are in the right boxes. The other way is machine vision. So machine vision has actually helped automate this process significantly because machines are able to do what humans can't in terms of size and scope and speed. Both of these processes, though, have severe limitations. Number one, manual inspection, there's human error, right? You're relying on people, and inevitably people get fatigued and tired, especially when dealing with high levels of accuracy. There's also volume limitations. When you're producing thousands of parts, you can't possibly check everything, and we're required to then rely on sampling, which doesn't always work. It's a very time-intensive process. There's an increasing skilled labor shortage around the world, and it's very hard to track data, which, as we all know, is becoming one of the most crucial components to actually implementing smart solutions across the entire footprint of the factory. So whereas machine vision has been, it also has limitations. One, machine vision systems have very limited function. So if you purchase some machine vision camera equipment, it will do very well at its specific function, but that's it. If you need to then apply, you want the same process or multiple levels of inspection to take place in the same place, you need to buy new equipment. And often that equipment is very expensive. And that's difficult when you're trying to grow and scale. Plus, hardware integrations can be difficult. And there's often long deployment cycles. And even though there's greater tracking of data, it's often difficult to access that data because it could be inside of one particular system. So these are some of the limitations. Now let's look at what happens as a result. So the impact of inefficiencies in the current quality management systems. So number one, material and labor costs are going up because you're spending more money on parts that you're not using. Labor costs are increasing as factories are forced to rely on people that are often not as efficient as they could be. Lead times go up. And then if you're late for delivery, there can be penalties under the contract, or there can be fines set by law at times. This also results in decreased yield, decreased revenue, and this can affect customer relations as well. So it's hard to actually quantify this, especially because if you're just looking at hardware products that are lost, seeing the actual impact this has throughout the business is difficult. But there's some experts and consulting firms that have done assessments on what the average is, And although it varies by industry, 10x the cost of scrap is one way that, one average for quantifying. The other is companies are often looking at 15% of their operational expenses are wasted because of quality management issues. How many manufacturing companies here today or people in this sector would love to have a decrease of 15% of their operational expenses? And that's what we're often losing. So, what's the revolution? What's the next step here? It's visual inspection with machine learning. And there's a lot of definitions for machine learning and AI. I'm going to talk a little bit about that. But for today's purposes, when I'm talking about machine learning, I'm really talking about combining computer vision with AI together. So what we're able to do when we can combine computer vision and AI is, number one, inspect with cameras, inspect for dimensions, text, defects, basically anything that can be identified through visual inspection, we can now identify with high levels of accuracy in near no time. And when you add the machine learning component, the technology is able to actually learn and adapt to be able to more effectively identify those issues in the future. And next, the business can then grow as a result. And all of this can be done with no major changes to existing manufacturing processes, without complex hardware integrations, but taking your factory as it is, without having to invest millions of dollars to restructure the entire thing. So, artificial intelligence, what is it? There are many definitions. In fact, no one can really agree on one definition. So if we take Encyclopedia Britannica, it's the ability of a digital computer or computer-controlled robot to perform tasks commonly associated with intelligent beings. This is the broadest definition, which really comes down to the idea of basically making computers act like people. The Oxford English Dictionary takes a slightly different approach. The theory and development of computer systems able to perform tasks normally requiring human intelligence, such as visual perception, speech recognition, decision-making, and translation between languages. I like this definition because it provides some granularity into some specific use cases that are often seen as the most common, but in some cases is actually a little bit too narrow. Now let's look at a company that's doing this for real. This is Amazon's definition of AI. The field of computer science dedicated to solving cognitive problems commonly associated with human intelligence, such as learning, problem solving, and pattern recognition. Right? A slight variance. I'm going to offer you a different approach. I'm going to offer you a perspective that isn't necessarily one definition you can boil down to a sentence, but a different way of thinking about AI in the way that I personally find to be the most useful. It's the technological capacity to make independent decisions using a recursive model of deductive and inductive reasoning. So let's unpack that a little bit. So technological capacity, we're talking about artificial intelligence. To make independent decisions, that means that the computer can actually operate on its own without an operator once it's deployed, using a recursive model, so it has to have some sort of reciprocity, using both deductive and inductive reasoning. So let's unpack those last two, deductive and inductive. First, deductive reasoning. Deductive reasoning is the logical process where you're applying a principle or a rule of general applicability to a specific set of facts or data to reach a logically certain conclusion. So you know if you have a premise that is true and you take that as your first principle, when applied to data, that conclusion must be true. For example, if we accept the general premise that all men are mortal, and we know that Gandhi is a man, therefore it follows, to a logical certainty, that Gandhi must therefore be mortal. Now, let's look at inductive reasoning. Inductive reasoning is when you start with a set of facts or data, and you use those set of facts or data to actually extract a principle or rule therefrom, to then reach a likely conclusion that you do not know to a logical certainty, or to predict some future outcome. For example, so you all had the privilege of hearing from my dear friend Rajesh earlier, who I've volunteered on my own volition to use him as an example. So we know throughout history that how many men have died. We don't know to a certainty because it's possible that someone sitting here today could live forever. But we know that there are millions of men who've walked this earth who have passed away. We know that Rajesh is a man. Therefore, we conclude not to a logical, definitive certainty, but to a significant likelihood that Rajesh will likely die. Sorry, buddy. So, let's take this concept of deductive and inductive reasoning working together and think about how does that actually apply when we're talking about visual inspection. So, number one, machine vision. Machine vision, I'm going to compare as the existing system and then compare that to machine learning, which for these purposes, I'm talking about computer vision plus AI. And there's some nuances between machine vision and computer vision. Typically, machine vision are more hardware-based systems that have some software applications versus computer vision is more heavily on the software. And combining with AI, that's what we'll call machine learning. So, machine vision. This is an algorithm that applies man-made rules to visual data. So that means that humans have to actually create the algorithms and create the rules for the outcomes that they want to identify. So the defect detection is dependent on specific programming. You can look at object presence, counting a number of objects, the orientation of an object, dimensional analysis. Machine learning, on the other hand, this is an algorithm that applies a data set to build a model to create the rules. This is the idea of inductive reasoning and deductive reasoning working together. Because instead of starting with the actual premise, we're taking the data and then we're extrapolating what the rules must be. This is actually the way we humans think. We're not born with a certain rule that we know as babies that what we know must apply to the world. No, as evolutionary beings, you touch a stove, you learn it's hot. You touch a stove, you learn it's hot. Eventually you realize hot stoves, they burn. You drink enough from enough rivers around the world, you learn water is wet. And then when you see water, you assume, I already know it's going to be wet. That's inductive reasoning. That's how computer vision and AI works. Defect detection evolves as the data set grows. This is a revolutionary concept because it frees up humans and allows systems to actually grow faster than they can. It's also a scary concept and the basis for many sci-fi films. So typically, you'll look at convolutional neural networks and unsupervised learning to build a model that can identify defects that are not specifically trained. This is a huge difference because it's one thing to identify the defects that we predict, but as all engineers know, it's the defects that we don't predict that can get us the worst. So I'll walk you through a brief example. So imagine this circle is a component, any component, and you're tasked with identifying that the diameter of this circle is of a certain size, which here I'm referring to as X. And you know that depending on the particular machine or the use of this component, there could be some margin of error that's acceptable. That margin of error could be millimeters for very large components. It could be micrometers, it could be nanometers. But often there's some sort of variance. What I'm going to do now is compare 3 scenarios to help illustrate the concept I just described. I'm going to look at, so here you see there's first a proper component. So if you imagine this is the edge of that circle zoomed in, and these dotted lines as x sub 1 represent the tolerance based on the diameter that's acceptable to the particular user. So as you can see, the edge of this component falls within the acceptability parameters. We'll call this as a proper component. The other defect we'll look at is if the component is too large. So again, if you imagine this circle is larger, and this is the acceptability parameter, x sub 1, the edge of the component exceeds the boundary. It would be defective. And then finally, this is what we'll call as an unexpected defect. So the diameter of the component falls within the acceptability parameters, but there's still a problem that we can see when we zoom in. This problem can represent many things. It can be that there's a chip, a scratch, some sort of damage, the smoothness of the surface, a color variance even. See this as representative of a number of defects that are unexpected, also not specifically trained. So, first, let's assume we're looking at a proper component, and we're going to compare manual inspection versus traditional machine vision and machine learning. So, with a proper component, with a manual inspection, if someone's using a caliper or some other sort of device, you'll confirm here with a proper component, it's within the acceptability parameters, and we call this as a true pass. This means that your test says it passes, and it's actually correctly passing. It's a true pass. Second, with machine vision. You take a basic camera system, traditional machine vision, and similarly, that would be able to identify that this also is within acceptability parameters. And same thing with machine learning. In all three cases, for a proper component, you'll get a true pass. Now let's take a slightly more complex scenario. As I said, the defect where the component is too large, where the diameter falls such that the edge is just outside of the acceptability criteria. So with manual inspection, if you're measuring with a caliper and the person's doing it properly, it would show X here, which means this is a fail because this component is defective. And this would be a true fail. And you'll get the same result when you use machine vision that's been trained to identify the parameters and machine learning. Now we get to the interesting case. What happens when we have a defective component with an unexpected defect? So, if you're simply measuring the component using some sort of manual inspection, like a caliper, and the defect is very small and something you were not properly trained for, you might see that the edge of the component falls within the acceptability parameter, and so you'll pass it along. But the problem is this is a false pass, because the idea is that this product is actually defective, but this isn't what the person was looking for. Similarly with machine vision, if all you're doing is measuring the edge of the component, what would happen is the user would have trained this machine vision to identify specific points that it will refer to as the greatest outside of this diameter to ensure it's within the line here. In this case, it is. So again, machine vision might give this a pass. But this is a false pass because this is incorrect. Finally, we get to machine learning. Machine learning will take the data set and not only assess the diameter of the component, but based on the data set increasing over time, a machine learning model can actually identify that this is not something that should pass, even though it meets the diameter criteria, because of the defect here. Be it the edge being too rough, the color variance, whatever it is. A very simple illustration to help you identify the difference between machine vision and machine learning. Machine vision, you pre-train the system to identify exactly what you're looking for, and if there's defects that you don't predict, they can be passed along to your customers without you knowing it. And with machine learning, the system will actually evolve to identify those types of defects without them even being programmed. So as you see, machine learning is the best of the three methods to actually give you, as the technology companies, the most assurances that your customers will be satisfied. So, I'll talk briefly about Lincode solution, because this is what we do, AI and computer vision. So the Lincode solution can identify objects, text, geometries, such as dimensional analysis, angles, axis tilts, right? Color variances, and damages, defects, scratches, chips, that sort of thing. Actually predict future errors and machine downtime by running those recursive machine learning models. And then finally, helps companies like you improve product quality, overall equipment effectiveness, and employee efficiency. Because by allowing machine vision systems to work more effectively, you can redeploy your workforce in ways that can be more efficient to help growth for the business. So here's an illustration to put to context what this looks like. Imagine here, this is a conveyor belt with different products being produced. What Lincode does is installs a very basic piece of camera equipment. No need for a $10,000 piece of machinery. Something like an off-the-shelf camera that can be installed exactly where the manufacturer wants to identify certain processes. Then what happens is the information can be deployed and operated at a local server or via the cloud, such that the Lincode system is compatible with any camera. Existing cameras that are there already, the system is accurate to 2 microns or less, and it can be deployed in any factory environment. So a lot of companies have tried to do something similar, and they work in a lab setting where it's perfectly clean, right? There's no dust in the air, no vibrations. But to actually get this to work in a real-world factory environment is very hard. We've also implemented automated AI training so that instead of humans having to take the time to train the large data sets, the computer actually learns to train itself. It's easy to integrate with robotic arms so that if it identifies a defective product, it can move that product automatically. And as I said, it can deploy on-premise or the cloud. And because it's a software system, and because of all these advances with the AI, the actual deployment cycle is very fast and very inexpensive, often less than 1 month. So here's a short video showing you, imagine the components are moving on the conveyor as the camera is flashing and taking a picture of the defects and the components as they pass by. On the dashboard, the user can see video and pictures, and on the right, you can see what's being measured as either correct or incorrect. Also easy to integrate with other sensor systems. Then what happens is the software can deploy through API to connect to robotic arms to then tell the whole system what to do with the different parts, be it defective or proper, or simply different parts that are all proper but go to different types of customer uses. So that's basically an overview of what I wanted to cover today. I don't know if we have time for, I think I go till 6, yeah? So if anyone has a question or two about what we're doing here, happy to take a question or two now. Otherwise, what we'll do is go to a tea break. We have some more presentations, and then we'll have a panel discussion. Anyone have a question? Please? Here, the question is basically, how do we give the intelligence to the system to understand what is a defect and what is not a defect, particularly in situations where it hasn't been specifically trained? So, from a general perspective, the way machine learning and deep learning models work is that they rely on a data set that we already know is proper or not proper. And for most deep learning models to work, they need thousands and thousands of use cases in the data set to be able to train. So for example, if I were to help you understand how a man should look in a suit, I could lay out a number of rules and talk about the way it sits on the shoulder, the way that it covers around the waist, the way the color balances between the different fabrics, and I could give you a number of rules. And then you could follow those rules, and if you do so, hopefully you'll look good. But if I showed you thousands and thousands of pictures of people wearing suits, and you got a sense for it over time, you developed an eye for fashion to say, yeah, I know that these people look good and this suit doesn't quite fit right. Maybe it's for one of the reasons that I trained on, or maybe I can't even tell you why, but I just know that it doesn't quite look right. So by analogy, that's the same principle that works for machine learning. By looking at a large data set and identifying, okay, what's proper and what's not proper, the machine learning system will actually identify and create algorithmic rules that you may not have even programmed to determine what is it about that suit that makes it fit properly versus not. A key difference with Lincode is that instead of relying on thousands and thousands of data sets, we've actually developed the ability to create those models with very, very few data sets. So instead of relying on public data on what certain components should look like, we actually train the system based on your particular components, taking a small number of samples and deriving the model from there. In terms of the juice of that question, right? But how? How can you identify those rules based on such a limited data set? My friend, I'm afraid I'm going to have to disappoint you there. That's the secret sauce in our current patent-pending technology. But I hope that gives kind of an overview in terms of the general concept as to how it works. I should say also we have some demos running, a few of us here. Some of you may have seen them, and they'll be running later, I think, during the cocktail reception. So you can actually take a look and see some examples.